Hello students, in this video I'd like to discuss about strongly connected components. A directed graph is strongly connected if there's a path between all pairs of vertices. So this strongly connected term is always related with directed graph. If there's a graph in which there's a path between all pair of vertices, then we can say such graphs are strongly connected. A strongly connected component of a directed graph is a maximally strongly connected subgraph. I will try to explain this definition with the help of an example. We just consider this graph. Here if you notice this graph graph is not a strongly connected graph because there is no path from F to A or there is no path from H to C. But some part of the graphs are strongly connected. If you consider the subgraph ABE, that is strongly connected because there is a path between every pair of vertices in the subgraph which consists of vertices A, B and E. Similarly, F and G is a strongly connected subgraph, C and D is a strongly connected subgraph, and H, the single vertex, can also be considered as a single connected subgraph. So here in this graph it is not strongly connected, but certain parts are strongly connected, and here those parts we can say it as strongly connected component. So a strongly connected component of a directed graph is a maximally strongly connected subgraph. That means we can't say D itself has a strongly connected component because we have to include C. The subgraph is always maximal. That means the subgraph must contain maximum number of nodes or vertices. Okay, next is algorithm to find strongly connected components. Step 1 is call DFS of G to compute finishing time f of u for each vertex u. We already discussed about depth first search. So here this is our input graph. Here I applied depth first search and I calculate finishing time also. So I will get a table like this which contains discovery time, finishing time and parent. And this is the output forest of depth first search. So step 1 is the normal DFS that we already discussed. Step 2 is compute G Transpose. So this is the input graph. We have to compute G Transpose. G Transpose is nothing but we are changing the direction of each edges. Here there is an edge from A to B. So in G Transpose it will be B to A. Here there is an edge from E to A. Here there is an edge from A to E. Similarly all edges are reversed. So step 2 is to calculate G of T. It is nothing but reversing the edges in the input graph. Step 3 is the most important part. Call DFS of G of T. That means we are applying DFS in this transposed graph. But in the main loop of DFS, consider the vertices in order of decreasing f of u. So in the previous videos we discussed about DFS. There we considered the vertices in alphabetical order. Whenever we want to make a choice, we choose alphabetically smaller vertex. But here, when we run DFS on transpose of G, we have to consider in order of decreasing f of u. This table is as same as in the previous slides. So I just arranged vertices in order of decreasing f of u. So if you notice the f value is decreasing 16, 15, 14 up to 6. So I just arranged the vertices in decreasing order of f of u. So next I applied DFS in the G of T. So here I choose the starting vertex as A because when we consider the decreasing order f of u, A will come first. So choose A since A has the highest finishing time. Push A to stack, color it gray. Then we have to look at the adjacent vertex. Only adjacent vertex is E, so push into stack. Here I have explained all the steps. You can go through the step. It is same as the DFS we discussed, but here the vertices are chosen based on the decreasing value of f of u. Earlier we chose based on the alphabetical value. Here there is no need to calculate discovery time and finishing time. Here I am calculating only the pi value. Pi value means parent value to construct the depth first forest. So this will be the output of DFS of G transpose. So step 4, output the vertices of each tree in depth first forest. So this is the output, the same diagram in the previous slide. So with the help of this table, we can draw the depth first forest. So I will get a forest like this, which contain 4 trees. So each tree can be considered as a strongly connected component. This is the same example we saw in the introduction slide. So A, B, E is a strongly connected component. F and G is a strongly connected component. C and D is a strongly connected component. And H is also a strongly connected component. So this finding strongly connected components is one of the application of depth first search. I hope you understood this video. Thank you.